So I'm going to do a talk on assembly language in Go. So I'll start off with a bit of an introduction as to my interest in assembly language and kind of a bit of background as to what it's used for in Go. Then I'll talk a bit about instructions, which are kind of the building blocks of any assembly program. And then I'll talk about functions and stack frames, how they grow, what the calling conventions are in Go, and how they interact with the runtime. And then we'd probably be running out of time at that point, but I'll talk a little bit about testing and portability and how to lay out code. I've got some code on GitHub that you could have a look at if you're interested in seeing how you might lay out a project that has some assembly in it in order to allow it to run with different compilers and things. So my interest in Go assembly comes from, so I work on the IBM Z Systems team, specifically doing open source ecosystem work for mainframes, basically on Linux on mainframes. And this is the new S390X target in Go 1.7, so I've been working on that. And this is that machine, in case you were interested, seeing it in the release notes. So this is the IBM Linux one, which runs those distros. It's a big, high availability, high performance machine, lots of redundancy in there, that kind of stuff. Yeah, so my kind of interest in Go assembly came from, okay, so we have to get Go to run on this machine. If you're going to port Go to a different architecture, you have to write an assembler, and you have to write a whole bunch of assembly to implement things like the runtime. So that's kind of my background. So what is the Go toolchain's assembler? So it originates from Plan 9 assembler, from the Plan 9 toolchain. I'm guessing that most of you know that the Go toolchain has its origins in the Plan 9 toolchain, and so it's just evolved from that. It's kind of a high level for an assembly language. There are some architecture independent mnemonics, like cool and ret, but there aren't very many, actually. There's some higher level abstractions within the compiler itself, but most of the assembly is fairly architecture specific, at least in terms of mnemonics. The assembly can do funny things, like it can expand instructions that you type out. So you might say add, and it might turn that into 4 instructions because you tried to add something with a big offset, so it puts something in a temporary register. And it's something you need to be aware of when you're writing this stuff because you might have certain registers being used in the assembly that is not necessarily obvious from what you're typing out. You can also do things like insert prologues, for doing things like stat checks and optimizing away unreachable instructions. So things like if you have some code which is never branched to, it'll optimize that away. And a key thing about Go assembly is it doesn't work with GCC Go. GCC has its own assembly language. It is not Go's assembly language. So if you're going to write assembly language, it's something to bear in mind. That if you try and compile it with GCC Go, it might not work. You might run into slowness if that's the way you're optimizing. But it does have some advantages over using something like CGO, which might well work in GCC Go, because you can migrate from different operating systems, whereas in CGO, you'd have to have a C library that was operating system independent. So it has some advantages like that. I quickly typed out hello world in assembly. I hope you can all read it. It's a little bit scarier than hello world in Go. I wouldn't recommend doing hello world. In fact, I'd highly recommend not doing calls at all if you can avoid it from assembly. So what do we use assembly for in Go standard library? Well, a big place it's used is crypto. So a lot of architectures have optimized instructions for doing crypto. So for example, Intel have the AES and NI instructions. On S390X, we have the CPACF instructions for doing lots of different types of cryptography. So those are implemented mainly for speed in assembly. I also have things like math, which is implemented in assembly because you have a lot of floating point instructions that map well to the sort of functionality that you get from the math library, such as rounding, stuff like that. Math big, similar thing. When you're trying to do things with carries, it's much more efficient to do it in assembly than it is to do it in Go. But there's also a lot of assembly in there to do functional things. So things like reflection. So when you have to set up a stack frame for a call to some arbitrary function, you have to insert some sort of shim to set up stacks for that, and that's all done in assembly rather than by the compiler. The runtime obviously has a lot of assembly in it to do things like when you start threads, initiating the runtime, that kind of stuff. CGO for shims between Go world and C world, that's all in assembly. All the low-level atomic stuff, that's all in assembly, so those are used for locks and even the high-level locking systems. And finally, last but not least, syscall package, which is doing syscalls. So yeah, and there's other projects that do use Go assembly as well. One that came up, I saw at GopherCon was Atman OS, which is an operating system built on top of the Zen hypervisor. Go running on top of the Zen hypervisor, which is kind of an interesting project using assembly to do that kind of interaction between Go and the hypervisor. So as well as performance, I guess what I'm trying to say here is there are other things that you might be wanting to use assembler for. Yeah. I'll use a few different pieces of terminology in the talk. This isn't all of it. These are just ones I thought might be useful to know. Mnemonics, just basically the name of an instruction. Registers, these are small chunks of memory, very, very close to execution units on the CPU. So you use them to hold temporary values, things like stack pointers, that kind of stuff. Immediates, which are when a number is encoded directly into an instruction, and also memory. Hopefully you all know what memory is. So I won't have to talk about that. But essentially accessing DDR for the most part. Okay, so now I'll talk a little bit about instructions. What I've done here is I've put together some word clouds, because there are a lot of instructions, and I have nowhere near enough time to talk about them all. So I'll go through a few architectures that I've picked out, and I'll try to talk around the different instructions that they have. So this is the AMD 64 mnemonics. As you can see, I've taken out MovQ. So MovQ is a 64-bit move. In fact, any instruction, I think, ending in Q on AMD 64 means 8 bytes. So it stands for quad. So on Intel, a word is 16 bits, 2 bytes, and then a double word is 4 bytes, and a quad word is 8 bytes. On all the other architectures, it's different. So you see Q a lot. You see also this 32-bit moves. The MOV OU thing is kind of interesting. So that's the when you do a 16-byte read, so the O stands for octal, moving that into an SSE register. And then finally, the other interesting instruction here is the ASENC one, which is quite big, given it's only really used in cryptography and hashing. But that's mainly because it's whenever you call encrypt or decrypt, it actually runs that instruction 14 times in an unrolled loop. So there's a lot of duplication of that particular instruction. So here's another one for ARM64. So some interesting stuff here. You don't have jump and call in ARM, although they do, actually. But they've been aliased to B and BL. And you'll find this across most of the other architectures. They use BL mostly. And that's because it's branch and link rather than a call, I think is the idea anyway. And another thing interesting about the ARM64 instruction set is that they have pre-increment, post-increment instruction modifiers. So that's the .w and the .p, which is very small somewhere. Yeah, so this is a PowerPC. which is an IBM one. And very big there, you see movdu. So this is very similar to the post-increment ARM64 instruction. A couple of things in there are the synchronization instructions. So those are used in the atomic operations on power. That's where they come up a lot. And last but definitely not least is S390X. So this is one I've been working on. So you've got things like add with carry, add C, add E, compare and branch instructions, which seem to be fairly unique to S390X. Yeah, so that's those instructions. So one thing you'll have noticed about that is there's a lot of move instructions. And these are kind of the most common instructions you run into when you're writing assembler. And so I tried to create this table of all the different move instructions and what they do. There's a lot of overlap between these names, and the names aren't architecture specific, so actually it's kind of strange that it's done this way, and I think it's just an evolution thing. But you'll see, for example, that on ARM64 and MIPS, they use U for unsigned, whereas on PowerPC, they used Z for zero extend, and then on AMD64, they used ZX for zero extend. So yeah, I guess there was some talk about kind of condensing this into like MOV2, MOV4, and things like that, which probably would make more sense. But in case you are trying to convert between different assembly languages, take a look at this, and it might help out with trying to understand what's really going on. So instructions in Go assembly, the data always moves from the left to the right. So in the first instruction, you'll see that add R1 to R2 and put the result in R2. Some architectures also have the 3 operand modes. So you'll put, say, for example, subtract. Subtract's a bit annoying because it has the thing that's being subtracted on the left, so that you could do, for example, sub 7 from a register, and that would work. Yeah, again, destination on the right. Always destination on the right. Doesn't matter what the underlying instruction set is really doing. Destination was always on the right in Go. You can also see I put in an immediate there, so you can do multiply with an immediate and a register. Memory operands, they can kind of look a bit intimidating at first, but essentially all it really is if you ever see a register in parentheses, it means you're dereferencing that register. And then any number next to that, you just add it to the pointer. And if there's another register with a multiply sign, usually by 1, it means you're dereferencing that register times by a scale. And the only scale on most of the platforms is 1. So I think AMD64, you can do a couple of powers of 2 there. And then we come to symbols. So symbols are kind of interesting. So you have this weird interpunct character that everyone complains about when they talk about Go assembly. And that's just a way of splitting a package name from a function name, but the package name is actually optional. So if you just put the interpunct there, you'll get a local variable. So if you had an example here, if you had that myvar variable, this is how you'd access it from assembly. And addressing these things, tend to use mov for this. So if you just put $1 in front of your memory operand, that'll take the address. You can also use the LEA instructions on AMD64 and LAY on S390X. I can't remember what the others are, but they do the same thing with it if you leave off the $. It's not really particularly important. But this is kind of a nice, relatively portable way of doing it. Branches in Go. There are 2 ways of doing branching. One is labels, and the other one is just doing relative to the program counter. I would always use labels for this. I've seen if you're using a program counter relative offsets, you get up to like 8 or 9, and then you start trying to insert the other instructions in code reviews, and you're trying to count instructions and trying to remember whether it's an offset of 1 or a -1 or, yeah. So I would limit those to kind of 2 at most, maybe 3 if you're really pushing it, but they can be useful in macros. So if you've got a macro in your code you can't repeat label names, so you have to use the PC relative branching. Okay. So when you're doing assembly programming in Go, you quite often run into the problem that a particular architecture doesn't have an instruction you want already in the assembler. So it's quite easy to work around this. You just add raw bytes into your instruction stream, and everyone's happy. So I've done that for this R instruction, so a bit piratey. I don't know what you'd use it for, really. But one thing to be careful of here is some of these architectures now have little endian and big endian versions, and the instructions encodings are different on the two. So what that word might make sense on a big endian architecture, like S390X, but if you're on PowerPC, you have to be careful because it'll flip them around, depending on which architecture you're using. So you might be better off using the raw bytes on those architectures. Okay, so now I'll just talk a bit more about function calls. So let's dive straight in. So the way assembly works is you have a declaration in your Go. So this is kind of like a C declaration. You just have the function prototype in the code, and it tells Go about the arguments that your instruction takes. If you've got pointers in there, it has pointer maps and things that so it knows whether they should be garbage collected or not, that kind of stuff. And then you have a .s file, which actually contains your assembly code. And these, for functions, use the text identifier to signify a startup function. Then you have a package name. And actually, most of the time, you should leave the package name off. So I think in the documentation, it says that it messes up the, I don't know if it's still true, it messes up the way it does pointer recognition in the function prototype. So you should probably leave the package name off unless you have a specific reason to use it. It can infer package names based on what folder it's in, essentially. Then you have the function name. Hope that's pretty obvious. All symbols in Go assembly are offset from the static base, which is like a fake register. I'll talk a bit more on fake registers in the next slide. But you can just think of SB as like it's a global symbol. That's kind of the way of thinking of it. Following that, you have these two numbers. You have the stack frame size, which basically says how many local variables do I need in bytes? What size of local variables do I need in bytes? And that's followed by an argument size, which is actually optional. But I suggest you put it in because GoVet can actually check to see if your declaration, your function prototype matches the assembly you've written, which is kind of useful behavior. And here we have two double precision floating point numbers, so we actually have 16 bytes. So I'll talk a bit more about that in a second. So here are the pseudo-registers. So you have the frame pointer, which is used for arguments. And I've got some pictures in a minute that will hopefully make it a bit clearer. And these are, we always have positive offsets to access your arguments. The stack pointer is always negative offsets, and this is for your local variables. There's also a SP register on AMD64, which is not the same thing as the SP variable virtual register. And this can be a little bit confusing for people, particularly if you're working on another architecture that doesn't have an SP register, and then all of a sudden on AMD64 people are offsetting from positive numbers from this SP register. So just something to bear in mind. And a static base, which we talked about already, just basically all named global variables are all offset from the static base. And the program counter, which we saw in the branching, which counts in pseudo instructions, so it's not real instructions in there. The calling convention, all arguments are passed on the stack. So there's no registers for arguments unless you've got a context, but I won't really talk about that now. The return arguments always follow input arguments, and I think they're always aligned to pointer size, but it probably depends on your architecture as to whether they need to be aligned to something bigger than that. But I think mostly it's pointer size. And that can catch you off guard. So if you say take a bool and return a bool, it won't be 2 bytes, it'll be 9 bytes or whatever. And all registers are call or saved. So this means the calling function is responsible for saving its registers. They will all be trashed, basically, apart from these exceptions, which are complicated in the runtime. So there's just a visualization a bit about this square root function. So you see we take x, move it into f0, destination on the right. We square root it, f0, destination on the right again. The result goes into f1. Then we move f1 into our result space on our stack. Right, so now we get into the fun bit. So to help you visualize this, I've kind of drawn out some stacks frames. And you'll see the reason that arguments are positive from the FP is because you're going up. And the reason offsets are negative from the SP is because you're going down. And you'll see that there's like return addresses in there and stuff. So we're on a linked register architecture. So this is every architecture apart from Intel, basically. You get this return address which you save at the bottom of your stack whenever you do a call. And so it's important to use these virtual registers because they allow you to ignore those return addresses. And if people decide later on to insert other things like frame pointers in there, you can ignore them and just carry on as you were using the virtual registers. And here's the same thing, but for 386 or AMD64. And now they have frame pointers enabled, so actually whenever you go into a function, it saves a frame pointer as well. But similar idea, really. You do a call, it saves the return address, and then it saves the frame pointer once it's actually in the function. And then you've got some local variables below that you can access using this virtual register. I guess the nice thing about this architecture is that you can access directly using the SP register, starting from 0, whereas a lot of other architectures, as you'll see, it starts from something lower. Okay. Right. So how do you use local variables? So we saw before that we have this number, 16, next to the $sign in the start of the function that says, this is the size of the local variables I have. And for the microsleep system call, you need to provide it with a time val struct. So those of you who are familiar with writing lots of C will know what a time val struct is, but basically it's just a 8-byte word for the seconds and an 8-byte word for microseconds in a struct. So what we do is we do some calculations with our 32-bit microsecond value to divide it by a million, take the quotient and the remainder, put them in these 2 slots. Again, you see using the negative offsets from the pseudo stack pointer. And then we take the address using the $sign and put that into our R8, which is part of the system call. And we can do our system call, and all those variables are all living on our stack. So they just go away once we finish the call. Another important thing to be aware of when you're writing assembly is stack growth. So in something like C, you just keep growing the stack most of the time, and you have what we call page faults and guard pages, and the stack can kind of keep growing. In Go, because you want lots and lots of Go routines, you want to start off with really small stacks. And so these are allocated on the heap bit as very small stacks. And the way we avoid going over the size of the stack is we have a little prologue in our instructions that says, okay, I've hit the edge, I need to create a new stack. We copy across all our old stack frames to this new stack, and we adjust any pointers on the stack because obviously if we have pointers to things on our stack and we're copying them across, we need to adjust all the pointers to point to the new stack. And then we can just garbage collect the old stack. And so you can carry on, and then it happens again, copy, adjust all the pointers, garbage collect the old stack, and then carry on executing. So for this reason, you also need to be very careful about not having pointers in your assembly because Go doesn't know where those pointers are. So basically try to avoid, if you're going to have, specifically it's if you do a call from your assembly function, you need to make sure there's no pointers in your local variables. So there's some flags to help you do this. For the most part, you don't really need these. Go's pretty good at detecting when it doesn't need to do a stack check or a frame check, or instead of a stack frame. But it can be useful for kind of documenting the functions and making sure that it doesn't insert stack check or allocate a stack frame. Most of the time, you should probably use no split because you don't need big stacks usually when you're writing this stuff. And yep, and those just go in the flag section of your function declaration. I just wanted to also mention escape analysis. So when you're writing assembly routines, Go can't tell whether a pointer that you put into your assembly routine escapes or not. And what this means is it has to assume it does escape. So it'll always go on the heap, it'll never live on the stack. And if you want to avoid this, you just use the Go no escape annotation. It's a little bit ugly, but there it is. And this just tells Go that any pointers that I take as arguments aren't going to escape. They're not going to go into a different Go routine or go into some global variable somewhere. They're just going to stay local to this function. So for example, here is memmove. You don't want every time you call memmove to have all the pointers being pushed onto the heap. And so finally, I'll just talk very briefly about testing and portability. So I've got like a little code layout kind of template that's based on what I've seen in the Go compiler. The main thing to bear in mind here is things like build tags, making sure you don't build on GCC Go, and the other thing is to make sure you have a nice generic implementation that you can use for testing against, and for architectures which don't support, which you haven't written a handwritten assembly for, and usually feed them into your tests so that you get good code coverage of your generic implementation as well as your optimized assembly implementation. And if you want to take a look, I put the link up there to kind of an example of this, so you can have a play around, adapt it to your architecture, see if you, hopefully I haven't made any mistakes, but probably have. And I think that's me. Thank you very much for listening. I'll be around if anyone has any questions.